Dr. Brady, you muted. Dr. Brady.
I'll tell him. I'll post in the chat.
Okay. Dr. Brady, you're muted. Hello?
Hello.
Dr. Brady?
Yes, thank you. Now you can hear me. Yes, thank you. What happened is the other machine, I lost the Zoom for a little while. Okay, if you can hear me, great, fine. We talked a few days ago about having a test Tuesday. And yesterday, if you were either here or home, not home, but you know what I mean by home, we questioned about what kind of test we should have. I asked you to think about it. Have you anybody got any ideas? You want to have an open book, open notes, everything, which I said by its nature, it has to be more difficult? Or do I trust all of you to be honest and take the test? Now, there's other things, by the way, is how long the test would be in either circumstance. As far as I'm concerned, I'm not worried about how long it takes you. So you can have all day to take the test if you want, with whatever format we decide. Okay, I don't think we should do it for 3 or 4 days in a row. In other words, I don't think I should give you a week to do the test or something. But I think you should do it on one day, but you can take a certain length of time. Others, I can put the test out there or whatever. I also think it's difficult to have 2 different days when you come in and have tests. That just takes us twice as long if we do it in here. So I think it almost has to be remote the way this is all, the way that COVID has done what it's done to us. So I've been talking, what do you think? Anybody from home or, I say home, I'm talking about remote, but I'm just not used to all the words. Sir.
With my situation, remote would probably be best. I am going on that.
Okay.
I would prefer to have a regular test.
Wait, stop. Let's see if I can turn you up. I've been turning you off all semester, so now I'll see if I can turn you up. Go ahead.
I would prefer to have a regular test that is not open book.
So a regular test that is closed book, closed notes, and she's claiming she would be honest.
I'm not saying I'm a not honest person, but I think for me, application's more important. So if I had the notes, sorry, for me, application is more important. I think if I had the notes and just worked harder problems to be able to apply them, I think that would be better all around for me personally.
Okay, so we got sort of two different opinions here.
Could you give us an example of the harder questions? Like, I mean,
Go ahead.
could you give us an example of the harder questions?
Not today. I mean, it's going to take us long enough just to do this. So you may not have heard him. He said he wants an example of a hard question. I don't know yet. Okay, I haven't made up either test. Once we get the test decided, then I can start telling you what's on it. Okay, but anybody else? Now, of course, this is America still, and we still go by votes and things, I hope. Anyway, I presume since there are two different opinions here, we could have a vote. And I presume everybody would agree to do whichever it is. And by the way, whatever we do on one test, if suppose we do the open stuff and it's hard and you might think, boy, I voted for this, but I'll never do this again. So the next time we do it, you might go the other way just because you think I was unfair to you or something. On the other hand, you might think, I know 5 people cheated, I'm not going to tell him, but I don't think we should do that again. I hope you do tell me, by the way, you find somebody cheating, because I like to torture people. Anyway, so anybody else have an opinion, or should we put this to a vote? Are you all registered to vote?
Yes.
Okay, so how do we do this?
The people in the chat could, or at home, could put a thumbs up if for what they want to vote for, and then everybody in person could just do it normally.
You say it, and then you guys at home can vote. And if somebody there wants to handle the chat and how many people do that, it's more difficult for me to do the chat from here.
You can just say closed or open in the chat and then count the number of responses for each.
I'm not.
Sorry, you could just put closed or open in the chat and then just count the number of responses.
Yeah, I know, but I thought we could just do it without normal. I can count you guys here, and somebody can do the chat.
We could just do all of the group me if that'd be faster. I mean,
What?
the group me we have, there's a way you can vote on the group me. So
Oh yeah, we could do a poll on the group me.
You guys at home decide how you want to do this. You want to do a poll?
Yeah, let's do a poll.
You see the trouble? You see why we don't have computers in the classroom? It takes forever. Okay. So, so as far as the people here, the person who suggests that we have an open notes thing is here. So we'll ask you how many people are in favor of that, and you guys can tell me at home, or I can set it up if necessary, but talking and playing with the machine just takes a lot longer for me. So how many of you would like to have an open notes thing? Okay, so I'm getting 1, 2, 3, 4, 2, 4, 5, 6, 7, 8, 9, 10, 11, almost everybody here, 12 people out of 13 would like to have the one, and that's close to a majority because there are 24 people in the class. So 12 people, that's half. So Anybody, let's put it this way, anybody there who is not with us today physically want to do an open notes?
I'd like to do an open note test.
Okay, then it's going to be an open book, open notes thing, okay? Is that all right? Anybody violently opposed to that? Oh, next thing will be what day, okay? And I know you have different classes, different days, and that changes which days you're going to be around. I cannot deal with all of that. We just got to decide sort of generally on a day, and you know, some people can be here Friday and some Wednesday and so forth. I can't worry about which is which and who's a favor and who not to. So I don't know you guys. Some of you I wouldn't recognize anyplace else because I don't know what you look like. So in a way that's fairest because I can't discriminate because of what you look like. I might like one mask better than another, but that's a different thing. Okay. I would think we could have a whole day to do this. I could put or more, I could put the thing up at night, some night, and you'd have until the next midnight or something to finish it. Okay. I've got several things to do before I'm ready to give you the test, really, several more things to talk about. I think Tuesday's a little bit early. That's my own self, but I want you guys to decide when you might like to do it. I think we should do it next week. Again, other classes probably had a test a week ago. It's okay. Don't worry about that. I'm the one that has to worry about that. But I would think middle of the week, toward the end of the week, you should be studying all the time. You know, what do you think? Wednesday, Thursday, Friday? I know. I mean, normally you give people Wednesday, Thursday, Friday. They always choose Friday. But what would be the best time for you guys?
Personally, it would be the best day would be Thursday for me.
Thursday?
Yeah, I think so.
Thursday? For the people here, I'm hearing Thursday. What about you guys out there?
I'm good on Thursday too. I'd rather do it later in Tuesday because I have other stuff going on. So
So are you saying no to Thursday?
I mean, yes to Thursday.
Yes to Thursday. Okay.
Thursday is fine. I prefer Tuesday, but
I haven't heard any no's to Thursday yet. Okay. So we'll worry about that at the beginning of the week. I will be telling you what's on the test in generalities. Okay. I have sometimes told people exactly what's on the test. It doesn't seem to help. It's not that the test is that hard, but some people don't hear. Okay. Let me talk about some math, if we got that out of the way. Any other issues? I think what I can do, just to get this out of the way, Dr. Brady, you're muted. Well, no longer. Maybe you'd rather have me muted. Let me see. I'm trying to get everybody who is here. So, anybody waiting yet? I don't see anybody still trying to get in. Interesting thing about Zoom is it's very difficult to get Zoom off of my screen. And it's very difficult to sign out of it, which makes me suspicious since it's owned by Chinese. And I don't mind that that's recorded. But the last period recording, I can't put a window in front of it. It insists on being in front. So maybe we'll have to zap somebody over in another country. In any event, what I want to do is take a screenshot of you guys. Selected window. Okay, so that makes an attendance for the ones who are not here. I don't know how to do an attendance for those of you who are here. We'll work that out in time here. Now, I want to go to a share screen. I'm going to find out where my screen is now. Okay, I want to go share the screen and put up for something just to kind of get it out of the way a little bit. So those of you who have your stuff here, pages, talking about material on page 7, 6 and 7. And so, again, we'll try to, I think you can see that. This we talked about a little bit about yesterday, and I just wanted to do it further. These examples, the next 3 or 4 examples on these pages are harder for students to think about because you just haven't done this kind of thinking very much. And so I'm gonna mention this page 6, I guess it is, this D function. And what I'm gonna do is put it on the board, and I'm gonna unshare the screen so everybody can see the board, okay? But we're just trying to define a function, and this is a function that depends on whether the x is rational. Rational numbers are what we call Q, real numbers are what we call R, and irrational numbers are all kinds of different letters. So I'm writing on the board what you at home see on your screen. And we have to decide on this thing, what's what. Now, the one I just wrote up here, I'm going to put 1 when x is rational and 0 when x is irrational. Now I'm going to unshare here for a minute. And so now you should be able to see, I hope, this thing, which I'm trying to write big. I know it's kind of dim, and I apologize. I wanted to get a whiteboard, but there's none available because I think a whiteboard with black ink would be better for the viewers, but I'm told we can't have one right now. So everybody else wants one too, I guess. So anyway, we're stuck with this for now, but I'm going to try to improve on it somehow. Don't know how to do that yet, but maybe we can move the camera closer or whatever. Anyway, if you look at this function, you can't really graph it because there's so many irrational numbers and so many rational numbers that any number, anything I put here is either rational or irrational. That's what the real numbers are made up of. So if I tried to plot this graph, I need to make a 1 for every irrational number. So if 1 is this high, if that's 1, then 0, the function value, d of 0, would be 1 because 0 is a rational number. So we got 1 point plotted. Now, if I took the number 1, it would also be 1. If I took the number minus a half, it would also be 1. So by plotting points, as long as I keep plotting rational numbers, I'm going to get a whole bunch of dots, okay, on a straight line, y equals 1. But there's lots of holes because between any 2 rational numbers is an irrational, between 2 irrational numbers is a rational. So there's no next to. If I'm standing on a rational number and I take any kind of step, I will not necessarily, there's no next rational number. That's one of the interesting parts about the real numbers. Now, if I graph the square root of 2, which is 1.4 something, I'm going to have it plots at 0. Okay, so if I have square root of 2 here, it's going to be 0. And if I plot all irrational numbers now, and I can't do all of them, but what you're going to get is a whole bunch of dots. And since I already drew the line, you can't see all these dots. And I'm not making a curve here. I'm just trying to indicate something different than the x-axis. It is the x-axis, but it's dotted. So what I'd have to do is erase all the rational points from the real numbers to see that. The trouble is you can't blow it up enough with a microscope to see it ever. It will always look solid. So the graph will look like a solid line and a solid line, even though it's not solid at all, either line. It's just when you look at them, the point is like a TV screen, the pixels, you can't get enough pixels to divide this stuff because of the number of rational numbers and irrational numbers. Everybody understand? Now, is this a continuous function or something? Well, continuity has to do with where you are. So let's take the number 1 and ask, is the function continuous at 1? Is there a limit? Whatever. Well, the epsilon delta stuff says, if you think your limit is 1, now, I presume everybody would think if d of 1 is 1, to be continuous, you got to get close to 1 with points close here. And I hope you can see that no matter how close I get here, there's going to be points that don't go up there. Okay? And continuity says when I get near enough, everything goes up within some distance. And all these points don't. So how will we make a proof? What you would do is take an epsilon band around height that if somebody declares they think the limit of d of x as x goes to 1 is 1, somebody thinks that, how can you show them they're wrong? Well, to say they're correct would be for every epsilon there is a delta such that, and so on. You've heard this now for a couple of weeks. What if that's not true? Then that means there is an epsilon. See, if it's not the case for every epsilon, then it is the case that for some epsilon, things don't work. The negation of everything does is something does not. That's why we did the logic. So if I can find an epsilon such that no matter what the delta is, there'll be things inside the delta distance that will not go up within inside the epsilon distance, then I can disprove the fact that the limit is 1. Now, that does not prove that there's no limit, it just proves the limit's not 1. But we'll get to that. Okay, so what you do is you take epsilon to be a half, or a fourth, or an eighth, or a 16th, or 1/10, or anything that's not going to hit all these. You make your distance smaller than ever getting to the x-axis. Then, no matter what delta we pick, there's points here that do not get within that region because they stay down here. Does that make sense? So what we have just proved is the limit's not 1, which means the function's not continuous. What about the limit? Would you think the limit might be 0? So somebody will say, hey, it's not 1, it's 0. Well, put an epsilon band around this height. Does everything near enough keep inside here? And the answer is no. All these things jump out. Therefore, 0 is not a limit. What about any other number? Well, I hope you can see, you put any other number. Suppose I think, oh, it's 13, you know, because I'm kind of weird. Okay. I think it's 13. You know, what part of Kansas do you come from? Anyway. Sorry. What kind of band would you have to put around 13 so that not everything would get in there? A band of 1 would work. Because now all of them are not in there. None of them are in there. So one could, and it takes a little time to do it, but one could show that there's no limit at 1. I'm sorry, at 0, no, at 1. Well, I hope you see the same argument works no matter where you start. So if I were trying to verify the fact that this is not continuous, you tell me what point, I would put a little band around, because half of them are going to be up here, not half of them. Some of them are going to be up here, some of them down here. Why did I say not half of them? Because it turns out that the number of rational numbers is a different infinity than the number of irrational numbers. We can discuss that sometime. There's a lot more irrational numbers than there are rational numbers, even though both of them are infinite.
Is that because the infinite number is basically 0 to 0.9, and there's going to be an infinite amount of point after that? So there's going to be...
Not exactly. It turns out that you have to decide first, what do you mean by the number of numbers? And once you decide how you count, once you decide what numbers are, then I can show you this, that we have what are called finite sets and we have infinite sets. The trouble is that infinite sets, it turns out, don't all behave the same way. like there is the same number of whole numbers as there are integers, even though you might think it's twice as many. We do not have, as humans, very good intuition about infinite sets. And it wasn't until the beginning of the 20th century that anybody had any good intuition about it. So we've only known how to describe these things for about 120 years, interestingly enough. And we can talk about all that at a different time, but right now, no. Okay, so anyway, this is this one function. This is on page 6, and I'm going to go back to the screen now, the share screen, because that's the easy one. Okay, and so basically that's what I was trying to say below that on page 6. And if you get to page 7, for example, there's another example that suppose we define things to be 0 if x is irrational. That's the same, but we define things to be x if x is rational. Now, again, if I get off the screen, sorry about going back and forth here, but how does the new definition compare to the old definition? Well, I'm not going to write it all. I'm just going to picture it a little bit. If I tried to graph it, this time I get a whole bunch of points on the x-axis. I would get a whole bunch of points on y equals x. Okay? And we'd have 0 if it's irrational and x if it's rational. So a half would go to a half, 1 would go to 1, 17 would go to 17, and so on. But the square root of 2 would still go to 0. So now what are you going to get? You're going to get a bunch of dots, lots of them, like this, all over the place. 0 would go to 0 because it's rational. And you would get a bunch of dots on here, a bunch of those. So this particular function is continuous at one point. The limit exists at one point. Where do you think that is? It's 0. The reason is, again, if I put a little band around here, what happens? All the 0 ones are in there, and the rational ones, okay? Anyway, this point is a place where this stuff comes together, and that's why there's one accumulation point. Only one place we can take a limit, and so on. So that's just a little different thing, and that's the thing on page 7. At the bottom of page 7, there's a much harder one. It's really described on the top of page 8, and that's where you're 0 if you're irrational, but you are 1 over q if the fraction is p over q. So 1/2, 3/2, 5/2, 7/2 on the real line would all go up to a half. 1/3, 2/3, 4/3, 5/3, 7/3 will all map up to 1/3. And so you can try to draw this. What you're going to get now, instead of this kind of a picture, is you're going to get some bands of things. Okay? And there's only a finite number at each level that are rational. Like there's only 2 numbers that, 1/2, 3/2, 5/2, and so on. Okay? Anyway, this turns out to be, I marked that on the bottom of page 7. This turns out to be continuous at irrational numbers and discontinuous at rational numbers, and so on. So those are harder things, are not by any means in the book. The book doesn't delve into this kind of stuff at all. But I think this will help you think about what we mean by limit and what we mean by the epsilons and deltas and stuff. It all turns out to have, once it came up in 1880, mathematicians we finally got something that makes sense, okay, that actually we can use. By the way, I might just tell you quickly, the first person who defined what a real number is was named Dedekind in 1858, not that this is a history class, but he worked out a definition because all definitions of numbers up to that time were geometric. And Chinese, Japanese, Arabs, Hindus, whoever, nobody had a correct definition in any civilization. It was all based on length, on geometry. Okay? and for the Greeks, Pythagorean theorem and stuff, but it's all based on geometry. So people tried in the middle of the 19th century to come up with a analytic definition of what a number is. And this gentleman did, 1858, but he didn't publish it until 1882 because he didn't think it was worth much. And he had the thing that we now say was genius, and he just didn't publish it because this isn't a big deal. Anyway, but from 1858 to 1882, he watched his colleagues around the world try to do it. And he knew he had it. I mean, he knew he had a way to do it, but no, and he taught everybody else with, but nobody else came up with it. So 1882, he decided maybe I should publish it because nobody else can do it. And so he did. Now, what he used in between to decide whether or not somebody's definition makes sense or not, okay, is the following criteria. If you tell me, if you come to me, we're colleagues, and somebody down the hall comes to me and says, I've got the definition, you know, I know how to do it. His statement was, okay, prove to me using your definition, okay, that the square root of 2 times the square root of 3 is the square root of 6. That was his test. And nobody else could prove that. Simple, what we might think of as a pretty simple fact. People believed it, but they couldn't prove it without resorting to geometry. Okay? So once he published what he did, it was like, this is it. I mean, people realized that he had the clue to what these things are. And today, there's also a man, his name is Dirk, there's also a person named Cauchy. You'll hear the name Cauchy a lot in this class in the future. He has another way of doing it. There's two ways that we accept today to do to define what a real number is. And one has to do with some sequences called Cauchy sequences, and the other has to do with what are called Dedekind cuts after his name, Dedekind. Okay, so you've probably not heard all that stuff. If you have before, you had a really good high school class, I think. We'll talk more about real numbers as we go and what their problems are. Okay, let's kind of review real quick here. What functions do we know are continuous? We know square roots are continuous. By the way, when I see you scratching or you rubbing your head and stuff, now that we're in class, I react to people because sometimes people want to talk to me. So when you scratch your head, I'll probably look at you, not because I think you have dandruff, but because I just react to one gentleman in the very back scratching his head. That's what I see when you're alive and I can see you. Usually I stare at lips and other parts of your face to see whether you're understanding. I get nothing back from you guys except, I'm getting kind of sleepy. But anyway, I'm hoping to keep you awake, but you can sleep if you want. This makes the test grading easier. Okay, polynomials. What are polynomials? Polynomials are powers of x and numbers times powers and things added together, right? So if I know that x, the identity function, f of x equals x, if I know that has a limit or that's continuous every place, and if I know the product of continuous functions is continuous, then x squared is continuous because I can think of it as x times x. X cubed is continuous because I can think of that as x times x times x, or prove first x squared and then do x cubed one at a time. You can build up, and if you want to do x50, you can do that with about 48 different things, or maybe you can get smarter and do x24 and 24 and 2, or 25 and 20. You understand what I'm saying? We can divide up a more complicated expression into simpler things that we know the answer to and put it together. What about numbers times functions? That's another theorem. So that's where 3x squared becomes continuous because it's the function 3, a constant function, continuous constant function 3 times a continuous function given by x squared that makes 3x squared that makes a continuous function, and the sums of them and so on. So we have polynomials, okay? You said root. The only thing we prove is square root. The book tells you, the book says law 6, law 8, law 10, if you've looked in the book. And by the way, when you guys do start looking in the book, if you haven't, you'll see how easy it all is. I would suggest when you look in the book that you copy the examples. Make sure you can do all the examples. Okay. Now, sometimes on closed book tests, I put the examples on the test. I won't be doing that. Well, I might do that to see if you read the book at all. First test, I might put an example on the test to see if you can tear the pages out fast enough to, while you're taking the test, to find the example. But I hope you don't take the test that way. I've had a student do that once, tear out pages in the class, the open book tests, and they didn't like a page, they just throw it out.
Wait, for real?
I hope none of you, when we used to have phone books and telephone booths, I hope you never tore a page out for a number that you saw on a page you liked. I hope you never did that. Okay? But people used to. They want to call me, they find Brady and tear off that page. Yeah. Okay, that's actually, I like that in one sense, and that is that nobody calls me except one person, that's good. But no, I hope you don't do things like that. People with phone booths, they had a better idea. They just took the phone. So you have phone booths now that only Superman can change it. So I don't even know what I'm talking about. There's a joke in one of the Superman movies that Superman runs to a place and it's just a phone on a little thing about this size, and you can't get in the booth to change. Anyway, he looks at the audience at that point. Like, comes out of character, show you that. I can't change. Rational functions. What's that? That's the quotient of two polynomials. When are rational functions continuous?
Everywhere in their domain.
Every place in the domain, and where is the domain? It's everything where the denominator is not zero. Okay, so let's talk about that a little bit more, because that brings up something else you're supposed to know about already, but maybe not, and that has to do with asymptotes. So if I had, let's say I have 1 over x minus 1 minus 1 over x minus 1, if this is my function, this is not exactly a rational function, but it does have the quotient of polynomials. Now, I hope everybody can see that. What in the world is the graph of this? And what's the domain of the function? Well, because I got x minus 1 denominator, domain does not include 1. It's all real numbers except 1. But if I ask you to take a limit of this function, what you're supposed to do, and I don't care where we go, but the bad point would be 1. Okay? If I told you to take a limit of this function, what I hope you have learned to do is always simplify the expression before you take a limit. You don't take a limit first, because the limit of the two pieces does not exist. And you don't say does not exist minus does not exist is 0 or something. Okay? Does not exist means you cannot use your arithmetic on the function. So you simplify first. If I simplify first, I look at this and I say, hey, this is, I just get 0. Now, what's the limit of 0? And the answer is now 0. Okay. Now, what if I went to 5? What's the limit of 5? So this 1 didn't affect it any. What if I went to 5? Now, if you want, these are continuous functions at 5. So if you wanted to, you could stick in 5 and get 1/4 minus 1/4 if that makes you happier. You'll still get 0. I wouldn't do that. I would still simplify first. But now you wouldn't be wrong because both pieces do exist. Okay? But in case you get 0 all the time. So what's the graph look like? Well, in a way, I've already got a graph. The x-axis is the graph, except that's false. There's a hole right here. The x-axis does not, the x-axis has 0 in it, but this function does not. The graph of the function would be the ray, the open ray from 0 to minus infinity, union with the open ray from 0 to infinity, not including 0. So why in the world would I even put that up there? Everybody knows it's 0. If I wanted to talk about the function with a hole in it, I've got to do something to tell you there's a hole in it. All right? If I just said 0, now what I could say is I could say f of x is 0 if x is not 0, and stop there. Because I've just defined the thing without defining it at 0. Sir.
Why is it not defined at 0 with the x minus 1 in the denominator? I would have thought it would have been at 1.
Oh, it's 1. Okay. Now, why am I making that mistake?
See if we're paying attention.
1 to see if you wait. 2 because maybe I'm just stupid. Okay. But one of the things that people do is you learn, as I said the other day, you learn that if I write 0 here, you get this, but if on your test I write 1 here, or say 13 or something, some people won't know what to do and they'll still say 1. You've got to always pay attention to where you're doing something. And see, I changed this around a little bit, but it's 1. This is where there's a hole. So what I said was wrong. I hope everybody at home saw I was making a mistake. I don't know why you didn't sound off over there on my machine. Okay? Now, there are times, seriously, when I will just make dumb mistakes. I have never met anybody who doesn't. Doesn't make me feel any better. Sometimes I will. Sometimes I'll do it on purpose. I'll let you figure out whether I'm trying to cover, I don't want to admit I made a mistake, or whether, you know, you can figure that out yourself. You can have that fun if you want. But the point is, I will sometimes do it on purpose. I will sometimes not do it on purpose. I hope you're not going to drop the class.
I'm not dropping it.
I'm joking. I'm joking with you. Okay. Yeah. Okay. I've told some people they can leave if they have to get someplace. So I hope that that's better than just not coming. But that's not it. Okay, what time is it? 15. Okay. Point is, I was wrong. Okay, for whatever reason. Be careful. But the point I think is still well made. Basically, there's a hole. And if I want a hole, I got to put it in. If I wanted the hole at 0, I should have done this. Now this is wrong, but okay. Now, where's the vertical asymptote?
If it's a hole, is there still?
If it's a hole, there is no vertical asymptote. Okay. But what if I would not do this? I just do this one part here. Now, I'm not trying to make any mistakes now. Okay. Now I've still got a problem at 0. So the domain still has a hole. But now I have a graph that's not just the x-axis. I've got some other points here. Okay. And what happens now? No, let me change this a little bit. I could have had x minus 2 over x minus 2 times x minus 1 first. For which you would say, oh, now there's 2 holes. But I can get rid of this hole before I take a limit. So in the graph's going to have a hole in this part of it when it gets near here. But this is still left over and I cannot get rid of it. So if the relationship between the numerator and denominator is the denominator goes to 0 if you stick the number in, but the numerator does not, that causes a vertical asymptote. And now I want to leave this in here in a minute, but right now that makes a line right through here and the graph cannot cross it. So whatever the graph looks like, and we're going to be learning about graphing, but whatever it looks like, it can't go to this because that would make a point here that doesn't make any sense. So the graph's either got to go up like this or it's got to go down like this. That's the only choices it's got. Now, I'm not drawing it to say it stays down here. I don't know what it's going to do because I'm trying to take the attitude that I do not know how to graph yet. I hope you guys know what the graph does look like already, but we can't rely on what you did before. I'm going to be teaching you that, or we're going to go through it. But you're going to find out that when you have a vertical asymptote, you're going to have things going to infinity, either both on both sides or on one side, not the other. or vice versa, you know? And, you know, so I don't get bored, my mind wanders and so on. And what it just made me think is, I remember an eagle in Africa and a Goliath heron. And the eagle landed because the Goliath heron was 2 feet from the water and it had a fish. So when the eagle landed, the heron put the fish in the water and stood there, and the eagle didn't move. So the heron lifted his foot to show he had nothing, put the foot down, lifted the other foot, showed he had nothing. Okay? I saw intelligence in that animal. He's trying to say, hey, I haven't got it. Interesting. That's what I was just thinking about when okay? Because this stuff bores me and stuff. Anyway, it's about 19 after, but what are horizontal asymptotes? That will be where you have horizontal line where the graph approaches that. And when does that happen? That happens when the limit is infinite. All right? So the vertical asymptotes happen where we might decide to write here, I'm trying to say things real fast here. We might decide to say this is plus infinity. That would be wrong in this case. We might decide to say that. That's one kind of a limit is infinite, where we have a finite thing we go to. Now, basically, this would be correct if I put a plus here. If I approach from the right, that would be true. So that means the graph is going to come down like that. All right. Anyway, but if I go to infinity, then we worry about the size of this and the size of the denominator. And in this case, this is a higher degree than this. That means 0 is going to be a horizontal asymptote. That means the graph of this is going to approach 0 way out somewhere. I don't know from below or above, but it's going to approach 0. That's what a horizontal asymptote is. So if you have we're out of time here, but if you have something like what I just wrote up here, x minus 3, x minus 1, x minus 2. When I look at this, this is going to have 0 as an asymptote because the denominator is a square thing, the numerator is a single. But if I have like x plus 4, where the numerators are 0 is where the graph crosses the x-axis. All right, that's what you studied in high school. Where the denominators are 0 is the vertical asymptotes. And in this case, these are equal. When you go to infinity or minus infinity, what you do is multiply in both cases here by 1 over x squared. When you do that, that changes this. I know we're out of time. It changes this to this product. Hope everybody can see this at home. I'm trying to go fast now. It changes this to this. And when you look at this thing, 4 of these things go to 0 when x gets big. What you're left with in the end is 1 times 1 times 1 times 1, which would be 1, which does not always happen. Okay? But you'll get something, and that's the horizontal asymptote. Now, I'll be talking more about that on Monday. One thing I want to ask you about, I'm going to stop the recording here just so we do.